Hello again, everyone. Welcome to our discussion of section 5.5. In this video, we will be talking about solving logarithmic equations and solving exponential equations. Now, in the previous video, we kind of touched on it. We used a few techniques that we will be continuing to use in this section. But on top of that, we will extend those methods and techniques to more detailed ones, and we will just do more examples with more details. The purpose of everything we've learned about logarithmic functions or expressions and logarithmic properties is to be able to solve equations that have log, natural log, or exponential function forms in them. As you know, with any kinds of other equations that we've solved so far before this point, the x variable or the y variable for which we were solving was on the same level as the other terms. What I mean is this. Suppose we had an equation like this, right? And we were interested in graphing this line, and we would give this x some value and calculate y, or we would give y some value and calculate x, or something like the x and y intercepts. But the point being that in all of these cases that we've been solving for the variable so far, the variable was on the same level as the other terms in the equation. But in this section, we will then look at how we can use exponential properties and logarithmic properties to solve equations that are like this. So equals 5. So where x is not on the same level as all the other terms, x appears in the exponent of the equation. Whenever we have this situation, we must involve logarithmic properties, or we must take the log of or natural log of both sides. So that's basically the technique we use to solve for variables that are in the exponent. Unless, of course, there are exponential function properties that would give us another technique or another option to solve for the x variable. But basically, this section is so important because it is the converging point for all the other skills and properties and techniques we've learned so far in this chapter 5, which has been about exponential functions and logarithmic functions. This section is one of the two last and converging sections, which means we're going to be using everything we've learned so far in solving these types of equations. Okay, so that's the overall picture behind what we will be doing in this section. Now, before we get into the details of that, I want to remind you to please take maybe, in this case, maybe an hour to skim through the textbook section 5.5 for this, in this textbook. But anyway, take at least 45 minutes, if not an hour, to look through this section in the textbook before you watch this video or before you attend class. Then, as you attend class or you watch this video, take detailed notes about things you see or hear that might be important to you, as well as things that might be of question to you. Then, go back to the textbook section, rework all the problems that have been solved in the book without looking at the solutions in the book. Do the same thing with the video and look at the problems I solve in the video, and before you see my solutions, write down your own thinking about how to solve these problems. Preferably, even the first time when you watch this video, even if you have not looked at the book yet, I hope you have, but if even you have not looked at the textbook about this material, please pause the video when I get to an example, write down your best answer, your best thinking. Don't take more than 15 minutes. 10 minutes should be ideal. And then watch the video and compare your solutions with the ones I give. And of course, complete all the homework assignments by the due date. That's the way to gain most benefit from completing the homework. And of course, review all the previous material, because mathematics is a cumulative subject, and solving these problems requires us now and then to remember everything else that we've learned so far, either in this course or in even previous courses. Okay, so let's begin our discussion here. Here we have again, I give a summary of what exponential functions are, which these are functions where you have the variable, independent variable in the exponent, right? These are exponential functions. So naturally, they're different. Because they're different than any other type of equation we've solved so far, the techniques to solve these types of equation should also be different, as we've been learning about some of those techniques with logarithmic properties, exponential functions, and especially in the last video, we did use some techniques that you should revisit, I think, if you're not confident that you remember those techniques. Now here's a summary in these two boxes. I've summarized, especially in the one on the left, I've summarized one of the techniques that we used in the previous video, which was if we were interested in solving for x, the exponent, then we wrote the left and the right hand side in the same base as much as possible. Then we concluded that if these two sides are to be equal, and if the bases are already equal, then the exponents must be equal. So we set the exponents equal to each other, and we knew the answer to the problem. Remember in the previous video when we were evaluating logarithmic equations or exponential equations, remember that? That's when we did that. So we have already applied this one, which says if these two sides are to be equal and the bases are already equal, then the powers, then we must have the powers also to be equal to each other. Okay, so we've already used that technique. Now, we introduced properties of logarithmic functions or equations in the previous video, right? So in this case, in this section, we will apply those to solve logarithmic equations. And this is in addition to, this is very similar to the base exponent property. But this is saying that if you have the log of some expression equal to the log of some expression on the other side of the equation, then m and n must be equal to each other. Because if their logs are to be equal to each other, then the inside, the m and n must be equal to each other. Okay? We will make use of this property or this relationship in this section also. It says, so in this note, I'm saying that before solving for x in the exponential equation, right? That means before solving for x that appears in the exponent of an equation, just like that, we must use the technique of taking either the log or the natural log of both sides. Remember when we were solving the equations before we got to log functions and exponential functions. Remember a lot of times we would divide both sides by some number when appropriate. We would add something to both sides when appropriate. Or we would subtract something from both sides when appropriate. In this section, we may have to take the log or natural log of both sides. So that's an additional technique that or an additional tool we now have in our toolbox to solve equations, except that this tool is specifically designed to solve logarithmic equations or exponential equations. Okay? And the purpose of that, of course, is that this will help bring down the variable x, right? Notice how x is up high in the exponent. So taking the log or natural log of both sides of an equation helps bring that x down to the same level of the other terms. And we already know how to solve for x when it's on the same level as the other terms in an equation. Okay, so that's the tool we use to do that. So here I'm just reminding you that sometimes we may be able to reduce an exponential equation to a quadratic equation. Do you remember what that is called? Do you remember? We've used this method before, but never before with exponential equations. It has a name that I've used at least several times, 2, 3, 4 times so far. But this time, we're going to be using it in the context of solving exponential equations. And this method was called IEDU, the U substitution method. Remember that? The U substitution method? Sometimes we may be able to use this method in the context of solving exponential functions to solve for the variable. Okay? This one says, always check your answers in the original equation to make sure that the solution is valid and within the domain of the function. Remember when we did that? Do you remember when we did this, when we got the answers, we had to check back? Do you remember? We did this with other types of functions. Do you remember what types of functions they were? This is why I keep asking you to review the previous material. We used the checking with radical equations. Remember when we had 1 or 2 radical expressions in an equation? Once we got our answers, we had to check back those answers in the original equation to make sure that both answers were valid. And if either one was not valid, we just tossed it out. The other case where we had to check our answer back in the original equation were the rational equations. Remember when we had fractions? So in that case also we had to check back in the original equation to make sure that the solutions made sense within the original equation. Here, this is saying the same thing, but one thing I need to add here, it says always check your answers in the original equation. I should add in the original logarithmic equation. Logarithmic equation, not the exponential equation. With exponential equation, well, when I come to think of it, maybe also logarithm, in very rare cases. For sure, we need to check the answers in logarithmic equations, no doubt about it. But with exponential equations, I think we better check, but that usually, the solutions are usually valid, but very rarely they may not be. And I think we have examples of that. So let me just say logarithmic first, and then also plus exponential equations. Okay. So now, in addition to radical equations, rational equations, we now have 2 more categories of equations where we need to check back the solution. And like I say, with logarithmic equations, we have to do it every single time. But with exponential equations, we do not have to do it every single time. With experience solving these, you know when and where you have to check and when you don't need to check. Okay, and I will talk about that when we get to it. Okay, all right. So let's begin having these things in mind. So number one, part A wants us to calculate the x in this equation. Now this is an exponential equation. And even the one in the bottom, in part B, we should use the base exponent property. Remember that? That was this property that says that if two sides of an equation are to be equal to each other with exponential functions, if the bases are equal, the powers must be equal. Okay, and that's a very useful property when we have x in the exponent. So here, think of how we can rewrite both sides with the same base, because if the bases are the same, that the powers should be the same. Okay, so in this case, we have 2 to the x, and 32 can be written as 2 to the 5th power. Can it not? Right? Can it not be written in this way, 2 to the 5th power? Now we have two sides such that the bases are equal. Then, if these two sides are to be equal, the powers must be equal. Right? Therefore, x equals, what should x be? Do you see it? X should be equal to 5. Right? That's applying the base exponent property. If the bases are equal, the powers must be equal. Okay, x equals y because the bases are equal. Okay, so by this simple example, and actually it's a very useful example, you should be able to solve part B without seeing my solution. Right? So now it would be a very good idea for you, and I strongly encourage you to start pausing the video before you see my solutions for each of the subsequent examples. And we have plenty of them. So I want to remind you once at the beginning, please, before you see my solutions, pause the video, write down your own solution on a piece of paper, then unpause the video and compare your solutions with mine. Okay, so I'm assuming you've already done that. On this side, we have base 4, right? Can we write the right side to some power of base 4? Absolutely we can, right? On the left, we have this expression. On the right, 16 is 4 squared. Okay, so if these two sides are to be equal to each other, and the bases are equal to each other, then we have no choice, but the powers must be equal to each other, right? So from that, the result is 3x minus 5 equals 2. Then this is a linear equation that we can easily solve for x, right? So 3x equals 2 plus 5. We're isolating x, right? Minus 5 is on the left. Let's move it to the right. When we move negative 5 across the equality symbol, it changes algebraic sign. So it becomes plus 5. Then 3x equals 7. And of course, is x isolated? No. How do we get it isolated? Divide both sides by 3. Right? So then we have x equals 7 over 3. I hope this matches the answer that you have on your own. All right. So next, we have this equation. Go ahead, pause the video, solve this, and then come back. All right. So now the base on this side is 3. And I ask myself, is there any way I can rewrite the right-hand side to some base 3? Let's see. So on the left, we have 3 to x squared plus 4x equals 1 over, what can we do about 27? Can we rewrite it as some power of base 3? Absolutely. 3 cubed, right? 27 is 3 cubed. Now we know we can rewrite this with negative power by simply flipping it. This is coming to us from properties of exponents. If you have forgotten the properties of exponents, either go back to the book section where we talked about this, or if you don't have the book right in front of you, you can Google this. Google properties of exponents, and then go through those properties. Make sure that you refresh your mind about them. But let me also do that here. In this case, there's a whole bunch of exponential properties of exponents. The one we're going to apply here is this. If you have some term to some power like m, you can write this out of the fractional form. So you can bring this out of fractional form by moving this up and multiplying it by 1. But in doing so, this power changes algebraic sign. So it becomes like that. So if you have 1 over 2 to the 5th, you can write this as 2 to the negative 5. You can do this with any kind of exponent in the numerator or denominator, but you have to make sure that it makes sense doing so. So, for example, if you have x squared and x to the 5th, right, you can either move this up and make it negative. You can either write it like this, like that. Oops. Like that. You can either move this up and change the algebraic sign from positive to negative and then multiply the bases, which means the powers get added. Or you can move this down. You can say x squared over x to the 5th is equal to 1 over x to the 5th times x to the minus 2 power. You can bring this down, remembering that you should change the algebraic sign to the opposite. If it's negative, if it's positive, becomes negative. If it's negative, becomes positive. Okay, and then you can then add those powers, and you get that. 5 minus 2 is 3. Or you can do this. If it's x like that, if you have that, and this, right? If you have this scenario, you can rewrite this as move this up, move that down, and change the algebraic signs. So x to the 5th over x squared. Right? You could do that. And then you can move this up and subtract it from that. So you could then do x to the 5th times x to minus 2 power, moving this up, it becomes that, and then x cubed, like that. Okay, these are properties of exponents. We've talked about these a long time ago. So if you don't remember them, you must refresh your mind about them. Okay, so now let's move this up. So, well, on the left we still have this scenario. Let's move this up. In doing so, remember to change the algebraic sign of the power to the opposite. So it was positive. When you move it up, it becomes 3 to negative 3 power. Okay. All right. So now the bases are equal. Remember the base exponent property, this property, base exponent property, that if the bases are equal, then the powers x equals y. Because that's the only way the two sides can be equal. If the bases are equal, then the powers must be equal. Okay? So that means x squared plus 4x must be equal to minus 3. Okay? I hope this is making sense. Now this is a quadratic equation. Let's move everything to one side and set it equal to 0 and solve for x. Minus 3 is on the right. When I move it to the left, it becomes positive 3. And the other side ends up with 0. Right? This is a quadratic equation and an easy one to factor, right? Factoring this. If you don't know how to factor, then you must use the quadratic formula. So you must have memorized that quadratic formula. But factoring this is a very easy, these are easy numbers, 3 and 4, right? Single digit numbers. So we should be able to easily factor these. And to do that, all we have to do is say x plus 3 times x plus 1 equals to 0, right? Because x times x, x squared. 3 times 1, 3. Where are the x terms coming from? The x terms coming from x times 1, which is 1x, plus 3 times x, 3x plus 1x is 4x, which is what we have here. So you can FOIL this and get the same result. All right, so now let's solve for each solution. We know by zero product property, we can set each one equal to 0 and solve for x, right? Zero product property says, this is again from the past, if you've been reviewing like I've been asking you to, you remember what that property is. We covered it way early in the semester. If you have two products like this that equals to 0, then either this product is equal to, this term is equal to 0, or this term is equal to 0, or both are equal to 0. That was the zero product property. Okay? You can also Google that. If you don't remember it, Google that and it'll come up. So then if this term is equal to 0, if this factor is equal to 0, if x plus 3 equals 0, then x must be equal to negative 3. If this factor is equal to 0, then x must be equal to minus 1. So these are the x values that will result from that. In this case, we really don't need to check because both of those answers should come out right. I mean, we can if you want. So minus 1 squared, if you check this, minus 1 squared is 1, plus minus 4, that's 3, that's minus 3. 1 minus 4 is minus 3, which is 1 over 27. If you plug in negative 3, then you get 9 minus 12, and you end up with minus 3 again, and this checks out again. It's equal to 1 over 27. So with exponential equations, usually the answers are valid. It's the log functions that we need to check every single time. Okay, this equation, again, please pause the video and come back to it after you are done with your own solution. Okay, so I'm assuming that you're done with that, and now you're back. So here, thinking about, can we rewrite both the left and the right sides with terms that have the same base but different powers, just like this? Can we do this, use that technique to have the same base and different powers? Can we do that with this situation? Can we do that? We certainly cannot, because 28 and 10 cannot be written to the same base and different powers. So then what can we do? Well, we can, in this case, we can take the log of both sides, right? So to bring the x down and solve for x. So let's do that. So log of 28 to base x is equal to log of 10 to power negative 3x. Okay? So then on the left, remember the properties that we learned about last time, in the last video? That power can come in front, right? So x log of 28 is equal to minus 3x times log of 10. Okay? Now, one of the properties we had in the last video that we introduced said that log of 10 is equal to 1. So let's write that down. We know from the properties, from the logarithmic properties, that log of 10 equals 1. Right? Log of 10 is equal to 1. So let's replacing that into that equation. Therefore, what do we end up with? We end up with the left side, which is x log of 28. X log of 28 equals minus 3x. Okay? Then the x and x can cancel out. And we end up with log of 28 equals minus 3. Right? Is this true? No. So no solution. Therefore, no solution exists. Okay, in this case. Okay, so then, because log of 28, so log of 28 would be, we can calculate that. The log of any number that is between 0 and 1 is a negative number, not log of 28. So log of 28 is equal to 1.447 and so on. So the left and the right are not equal. So in this case, we have no solution for that. Okay. Then this one, again, please solve these two equations. And so pause the video, solve these two, and then come back to the video. Okay. All right, so I'm assuming that you've done that. All right, so we have, in this case, is there any way we can rewrite the right side to some to a power of base e? No, that's not possible, right? So what else can we do? Well, we can take the natural log of both sides to bring this 4t down and solve for t. Okay, so let's do that. Why did I take log of both sides here? And why am I taking the natural log of both sides here? It's because the base here is e. Whenever the base of a power or an exponential function, let me repeat that, whenever the base of an exponential function is e, I will take the natural log of both sides, because it makes things easier, and you'll see in a few seconds, you'll see exactly why. Okay, so natural log of e to 4t power is equal to natural log of 200, right? Taking the natural log of both sides. That side we can then calculate with our calculator if we are allowed to do it. On the left, though, can we simplify this? Absolutely. This 4t we learned about a property last time that says this exponent can come in front. So 4t times natural log of e equals natural log of 200. But we know from the properties again, right? One of the properties we learned last time said that natural log of e is equal to, do you remember what property that was? 1. That's why it's simpler if whenever we have a base of e in an exponential function, we take the natural log of both sides, not the log. So if you take the log, it's not incorrect, it's still correct, but you're going to have to use your calculator, and log of e, you're going to end up with some other number that is not equal to 1. But that the other side would also be log of 200, okay? So whenever the base of an exponential function is e, it's better to take the natural log of both sides, okay? Because of this, because now it's much easier. All right, so because of that, then we have the left side, we have 4t equals, right, 4t times 1 is just 4t, equals natural log of 200. So we're solving for t, which means we need to isolate t. Is t isolated? No, it's got a 4 right next to it. How do we get rid of the 4? We divide both sides by 4. Right? What do we end up with? We end up with t equals natural log of 200 divided by 4. Now, on an exam, if you're allowed to use a calculator, you certainly calculate that to some decimal value, whatever the problem is asking you. For example, the problem might ask you to calculate this number to 2 decimal places or 3 decimal places. You can do that. But if you don't have access to a calculator on an exam, or if you're working on the online homework assignments and the assignment is asking you to enter an exact value, this is an exact value. So you do not have to calculate this with your calculator. That, giving your answer like that, natural log of 200 divided by 4 is an exact value. Let me write that down. This is when people or computers ask for exact value, that's what they mean. Exact value. They mean, and give your answer either in this form, or if it's something like if it's like 1/2, you can also say 0.5, because in that kind of a fraction, 1/2 and 0.5 are both exact values, right? But in this case, let me calculate this with my calculator. Natural log of 200 divided by 4. Let's see what we get, right? So natural log of 200 divided by 4. Look at that, right? That's not exact. I mean, you can round that to 1.32 or 1.3246, depending on how many decimal places somebody asks you to round your numbers to, your final answers to. But most likely, you'll be asked to give the exact answer, and that is the exact answer. Okay? So I can actually say either that or give that answer up to 4 decimal places. So 1.3246, right? So or 1.3246. Okay? Either this or that, depending on how you're asked to give the answer. Okay? Like that. Okay, so I hope this agrees with the answer you already got on your paper. If so, please answer this question. So pause the video, answer this question, and then come back to the video. Okay, I'm assuming you've done that and you're back ready for you comparing this with your own solution. So once again, can I write the right hand side to some base of e to some power? No. Right? We cannot write this to base e of some number. No. So then what else can I do to solve for t? Well, t is up in the exponent, right? To solve for t, we need to bring it down to the same level as these numbers. What technique do we have to help us achieve that, to bring the t down? Well, we can take the natural log of both sides, right? Because, why natural log? Because the base is e. The base of this exponential function is e. So we can take the natural log of both sides. So let's do that. Natural log of e to minus t power equals natural log of 0.04. Okay? So now on the left, we know we have a property that says we can bring this exponent down, and that's what we want. So minus t times natural log of e is equal to natural log of 0.04. Now we know that this natural log of e is 1, don't we? We know that. So minus t times 1 is minus t equals natural log of 0.04. So we're solving for t, which means we need to isolate t. Is t isolated? Is it? No. It's got a minus right in front of it, right? So it's not isolated. So how do we get rid of this minus? We multiply both sides by a minus 1. Multiplying both sides by minus 1, we have t equals minus natural log of 0.04. Okay, you can either leave your answer like that, or you can, so that's the exact answer. If you're asked for an exact answer, that's how you would give the answer. Okay, this is the exact answer. Okay, what if they ask you to calculate this and give it to certain decimal value? Okay, let's see how we can achieve that with our calculator. So natural log of that, well, that number is between 0 and 1, right? What did we learn about in the last video or in the last class? What did we learn about taking the log or natural log of values that are between 0 and 1? We learned that if you take the natural log or log of numbers that are between 0 and 1, you get a negative value. So natural log of that is going to be some negative value. Then multiplying it by a negative out in front here, we're going to get a positive value. So let's see. Natural log of 0.04, right? I'm just calculating that piece. You get that, right? Minus 3.2189. Let's round it to 89. So we get, but that then minus in front here, this minus in front will make that minus positive, right? So we have t equals positive 3.2189. Okay, like that. Okay. Here, it says, again, we have an exponential function, right? So with t, we're asked to solve for t, and t, where is t? T is in the exponent. So we know, because the variable for which we are solving is in the exponent, we must involve log or natural log functions, expressions, right? Which one would you use then, log or natural log? It's better to use natural log because the base of this exponential function is e. All right. So, but to solve for t, look at how many things we need to go through. We need to go through this 1000. We need to go through this e, base e, and we need to go through this 0.09. There are several things here that we need to do before we can isolate the t and solve for it. Now, the technique for getting rid of any of these terms, it's not going to be the same. It's going to be a different technique. So let's begin from the outside, right? Our objective is to isolate this t by itself. Now, how can we get rid of this 1000? We can divide both sides by 1000. So let's do that first. So dividing both sides by 1000, right? And our objective is to get to t by itself. The 1000 and the 1000 cancel out. On the left, we end up with e to 0.09t equals 5, right? So the 1000 is gone. Now we have reached to the base of this exponential function, e. Okay? And the t is up there. We need to bring it down. What technique would you use to bring the t down? Would you take the log of both sides? Not bad. But it's easier if you take the natural log of both sides. Natural log of e to 0.09t equals natural log of 5. Okay, so you shouldn't forget to take the natural log of both sides, not just the left, but also the right side. Okay, so now we have that property that we learned about in the last video, and that says that we can bring this down and in front. As long as we have a log or natural log, we can bring the exponent down and in front. So we have 0.09t times natural log of e, right? Equals, sorry, let me straighten this out, equals natural log of 5. So on the left, natural log of e is 1. We know that, right? That's one of the properties we learned about last time. So 0.09t times 1 is itself 0.09t equals natural log of 5. Okay. So is it cool enough or what? When you take the log or natural log of both sides, is it cool? Because it simplifies the expression. It's awesome, isn't it? So now we go from that expression to this, which is a linear equation. It's just an equation with everything, all the terms on one line, along one line, with no exponents, so we can easily solve for t. So t needs to be isolated, right? What is preventing it from being isolated? The 0.09. How do we get rid of it? What's the technique to get rid of 0.09? We divide both sides by 0.09 to isolate t. So we end up with natural log of 5 divided by 0.09. So this is an exact answer. Exact. If anybody asks you to solve a problem like this, when I say anybody asks you, I mean either the online homework assignment, or if I ask on an exam question, let's say. That's what I mean. I mean, leave your answer like that. Don't calculate this with your calculator. Leave it like that. This gets full credit. That's an exact answer. But if I ask you, or someone, or the online homework management system asks you to solve this and give it to some decimal value. Say, calculate your final answer to 3 decimal places, right, let's say. Then you would use your calculator. So let's do that now. So we want to calculate natural log of 5 divided by 0.09, right? So let's see what do we get. We get 17.8826. So I said 3 decimal places. So let's round this to 17.883. Okay. So T is equal to 17.883. Like that. So either this or that. Or that. Okay. Is this clear, guys? I hope it's clear. If you're just watching this video and you're not in class, then I don't know exactly unless you let me know with your questions. Okay. All right. So in the next problem, again, please pause the video, answer that question on your own, and then come back to the video. So clearly, I'm assuming you've done that, and now you have your own solution. So clearly, the bases of the exponential functions on both sides are not equal to each other, right? 5 and 4 are not equal. So we can't set the powers equal to each other. We can't do what we did earlier with these equations. Remember what we did with these? If the bases were the same, we could set the powers equal to each other and solve for x that way. We can't do that here because the bases are different, right? So what else can we do? Well, we can take the log or natural log of both sides. So should I take the natural log? We can. Or should I take the log? Well, I'd like to take the log, first of all, because I've already applied natural log several times. So I want to show you that the log works the same way. And also, I'd like to apply log because the base of this exponential, both of these exponential functions, is not e. They're not e. If even one of them were e, I would use I would take the natural log of both sides. But neither one is e. So I'll just say, let me use log. Okay? But you can, if you want, you can take the natural log of both sides. That still be correct. But the point being is now using the natural log would not give you an advantage. It's just the same as if you would use log. But previously, taking the natural log of both sides gave us the advantage of simplifying this term to just 1. That's why. All right. So taking the log of both sides, log of 5 to x plus 2 power equals log of 4 to 1 minus x power. Right? One of the most common errors that I see on exam papers when I give questions like this is that when people bring this, well, let me show it to you and you tell me what's wrong with this, right? Let me make an error. So here's the most common error that I see people do. So they remember to bring this down, the exponent down and in front. But there is an error here. Do you see where the error is? What you see right now is the most common error I see on exam papers of you guys. So at least 40 or 50% of the class, at the very least, will make this error. Can you find the error? Do you see what it is? Well, the error is this. When they bring this down, the way this is written is just going to multiply 2 by log 5 or minus x by log 4. But this exponent has 2 terms, not 1. It has more than 1 term in it. So when you bring it down, you must remember to put the parentheses around it. Okay? You must put the parentheses around it. So what's the advantage of, what's the meaning of this? Why is it so important to put parentheses around this? Well, it's because now, by putting parentheses around 2 terms, you're saying that this log of 5 distributes itself to not just 2, but also x. But before you put the parentheses, log of 5 was set to distribute itself just to 2, but not x. On this side, without the parentheses, log of 4 was just set to distribute itself to negative x, but not 1. So do you see, you would have, if you forget the parentheses, you're going to generate 2 errors, one on this side and one on that side. Okay, so now let's distribute log of 5 to each term. So we have x log of 5 plus 2 log of 5, right? Log of 5 distributes itself to both terms. On this side, log of 4 times 1 is log of 4, minus x times log of 4. Okay, so now we're solving for x, but how many terms do we have this variable that we're solving for? How many terms? Is it 1 term? Is it just this? No, there's another term on this side with x in it. And we're solving for x, and it appears in 2 spots, not 1. So what happens now? Well, the next step, we need to bring all the terms, whether we have 2, 3, 5 terms with x in them, however many terms we have with x in them, we need to bring all of those to one side of this equation and send anything that does not have x in it to the other side. Okay, so let's do that. X log of 5. Let's bring this minus x log of 4 to the left. When I do that, this minus becomes positive. So plus x log of 4 equals, the log of 4 is already on that side. I'm not going to bother it, but I am going to send this this term to the other side. So because it's a constant with no x in it. So it was positive on the left. When I move it across the equality symbol, it becomes minus 2 log of 5. Makes sense so far? I hope so. So now what? Because we need to isolate x, but x is scattered between 2 terms, not 1. So what do I do now? Well, in order to isolate x, in order to get it by itself out of belonging to 2 terms, is factor it out. So x factored out, we get log of 5 plus log of 4, right? Remember, factoring is the opposite of the distributive property. So if you factor this right, when you redistribute the x into these 2 terms, you must get these previous 2 terms. Will we get these if we distribute the x? Let's see. X times log of 5, x log 5, plus x times log of 4, x log 4. So yes, the factorization is in fact correct. On the other side, we just have log of 4 minus 2 log of 5. So we can use properties of logarithms to make this a little more compact. But that would, I think, make this more complicated. So keep this as it is for now. So log of 4 minus 2 log of 5. Okay? So we're solving for x, which means we need to isolate it. Is x isolated? No. It's got this whole thing multiplied by it. So what do we need to do to get rid of this whole thing? We divide both sides by this whole thing. So let me do that here. Up here. Okay. All right. So then x, that means we want to divide that all of that by log of 5 plus log of 4. That's what we're doing. That side by log of 5 plus log of 4. Okay? And on the left, we end up with just x. On the right, we end up with log of 4 minus 2 log of 5 divided by log of 5 plus log of 4. Okay? So that's one way of leaving the answer. That's one way of leaving the answer, like that. Okay? Another way is, so this is an exact form. You can use some of the logarithmic properties we've learned to write this in a different ways. For example, write this as log of 25, because this log of 4 minus log of 25, right? You could do that too. But this would be an exact form. And you don't want to make this complicated. If you rewrite this as a complex fraction, if you apply that property we have, that would convert a subtraction problem to a division problem, you could rewrite this as a complex fraction, but that would make things more complicated, not easier. So that's why I'm avoiding that. So you can keep that as the exact form, or you can calculate it if you want to. So x log of 4 minus log of 25, right? We can do that. We can calculate that. So let's see, log of 4 minus log of 25. And 25, because you can, by the properties that we have, you can put this 2 as a power of this, so that becomes minus log of 25, right? Log of 5 squared. Or you can calculate log of 5, multiply it by 2. It makes no difference. You get the same result. So log of 4 minus log of 25, or minus 2 log of 5, is this quantity. It's minus 0.79588 divided by log of 5 plus log of 4. So let's calculate that. Log of 5 plus log of 4. What do we have? We have that 1.30103. I'm rounding that 2 to 3. And then, of course, this divided by that, we get the result, right? So minus 0.79588 divided by 1.30103. And we get that, minus 0.6117. And that's just approximating the answer to 4 decimal places. Okay. You can then plug this in there and see there's going to be a rounding error. So when you plug this x in here, you are going to get some error because I rounded that number, right, as you saw. But it's the left side and the right side will be equal to each other. Okay, I'll leave that for you guys to check. But just keep in mind, because this is not an exact answer, when you plug this here to compare the left and right, you're going to get a little bit of an error. So the two sides are not going to be exactly the same number, but they will be very, very, very close. Okay? All right. So now we get to the next problem, which is this. And go ahead and solve this before you see my solution. Okay. All right. So we have two exponential equations, or two exponential expressions set equal to each other. So can we rewrite this with the same base on both sides? No. We can't write 5 as a base of 2, right? So what we have to do is take either the log of both sides or the natural log of both sides. But would you take the natural log of both sides? You could if you want to, but I wouldn't, because neither one of these bases is e. If even one was e to some power, I would take the natural log of both sides. But in the absence of base e, what I'm going to do is take the log of both sides. So log of 2 to exponent x plus 1 equals log of 5 to exponent 2x. So that means we can bring this down, right? This exponent. Okay, is there an error in this? Do you see the error? What did I do wrong? Well, the way I've written this, log of 2 would distribute itself to just 1. But this exponent had 2 terms in it, not just 1, so I must remember to put the parentheses around it, which indicates that the log of 2 must distribute itself to both 1 and x. Okay, so let's do that. X log of 2 plus log of 2 times 1 is log of 2 equals 2x log of 5. We're solving for variable x, but x appears in not one term, but 2 terms, right? Here and here. Well, solving for x means we need to isolate it by itself. So what should I do now? Well, I need to bring all terms that have the variable I'm solving for, which is x in this case, to one side. They can't be on opposite sides of the equation. I want to isolate x, so I need to bring this term to the left, so x log of 2. This whole term was positive on the right. When I move it to the left, it becomes minus 2x log of 5. What about the right side? Will it get 0? No. We have a constant on the left. Let's move it to the right. This constant was positive log of 2. When I move it across the equality, it becomes minus log of 2. It changes algebraic sign that it has in front. Okay, now we're a little bit closer to solving for x, but not quite yet, right? Because x is far from being isolated right now. So what do I need to do now? Well, factor out x. So let's do that. X times log of 2 minus 2 log of 5 equals minus log of 2 on the right side, right? Is x isolated yet? No. We have this to get rid of, right? How do we get rid of this? Well, divide both sides by all of that. Log of 2 minus 2 log of 5 divided by log of 2 minus 2 log of 5. Okay, so this gets simplified, right? On the left, all of that and all of that cancel each other out. We end up with just x equals, right? X equals minus log of, I can put this minus in front. It makes no difference. This minus in the numerator can be placed in front of the fraction. Log of 2 divided by log of 2 minus 2 log of 5. Right? Can I do this? Can I cancel these two, log of 2 and log of 2? No, we cannot. A lot of people are still doing that. I don't know why. We cannot cancel this log of 2 by that log of 2 because they are being multiplied by, they are being, this one in the denominator is being subtracted from the other one. So let me use a scratch paper here and make a point. If you have x divided by x minus 5, can you cancel this by this? No. This x here cannot be simplified. Okay, so don't do that, please. Well, when can we cancel it? Well, only if negative 5 is being multiplied by x. So if you have x divided by negative 5x, if you have that, then you can cancel these two and you end up with minus 1 over 5. But this cannot be simplified because x in the denominator is being subtracted, 5 is being subtracted from that. It's not being multiplied. Okay? So please don't do that. Don't make that error. So now you can leave your answer like this, or if you prefer, you can, if you left the answer like this, it would be acceptable. Okay? Or you can leave, you can write the answer such that this minus is already inside the fraction. It's not dangling here in front. How can you do that? You can bring it down and distribute it to the terms in the denominator. So you can say either this or log of 2 divided by minus times 2 log 5, it's going to make it positive, minus times positive log 2 minus log 2. So that's the same, or x equals that. So that's the same answer written in a different form. Why? Because this minus, I took it and distributed it to the denominator. You could do that. Okay? So either answer is acceptable. Or you can calculate this. So this is the exact answer. This is the exact answer. If you prefer, you can also calculate it. With the calculator, we can calculate what that number is and write it down in rounded form. Okay, so let me do that here. So x equals log of 2 is that number. I'm going to keep 0.3010. I'm going to round the 2 to 3, like that. Divided by 2 log 5. So 2 times log 5, which is that, 1.39794. I'm going to keep up to 4. Minus log 2 again. Log 2 we calculated in the numerator is that. Let me move this a little bit. 0.30103. Right? So x is equal to this divided by that. So let me calculate all of that at once. 0.30103 divided by open parentheses and those two subtracted from each other. 1.39794 minus 0.30103. close parentheses, and we have that. And I'm going to round that to all the way to the second 4. So 0.2744. Okay. So you can either be asked to give the answer in exact form or this form. Either way. Okay, so here it is. We have another equation. Go ahead, solve this using your own knowledge and skill before you see my solution. I will give you a hint here, though. So let me give you a hint. Write the term that has negative exponent in terms of a positive exponent. So that's the only hint I would give you before you pause the video and solve this on your own. Okay? All right. So I'm assuming you've now back. You've already solved this problem and you're back, and hopefully the hint that I gave you simplified things. All right. So let me do exactly what I suggested, and I'm going to rewrite this with positive exponents. So e to the x minus 6 times 6, well, let me write it like this. 6 over e to the positive x equals 1. Okay? So all I did was rewrite that term with positive exponent. Now, let's bring everything to one side, the 1 also to this side. So e to the x minus 6 divided by e to the x minus 1 equals 0. Okay. Then let's take the common denominator. So taking the common denominator, the denominator here is 1, the denominator here is 1. Okay. Compare this denominator with this common denominator. What is missing from it? E to the x, right? The whole thing is missing. So multiply the numerator by e to the x. So we have e to the x times e to the x by the missing piece from its denominator. Minus, minus. Compare this common denominator with that denominator. Is there anything missing? No. So don't multiply minus 6 by anything. Just write it down. Keep it as it is, minus 6. Minus. Compare this, e to the x, with this denominator. Is there anything missing from this denominator when you compare it with the common denominator? Yes, the whole thing. So multiply the numerator 1 by e to the x. So 1 times e to the x. And the other side equal to 0. Okay. All right. So now let's simplify. On the left, e to the x times e to the x, because the bases are the same, this is the properties of exponents that we learned a long time ago. If you multiply two terms that have exponents, if the bases are equal, the exponents get added. So x plus x, 2x. Minus 6 is minus 6. Minus 1 times e to the x is minus e to the x. All of that over e to the x equals 0. Okay? All right, so now what? Well, we have a fraction. Nobody likes fractions because they complicate things beyond what's necessary. So let's get rid of the fraction. How do we get rid of the fraction? Do you remember what technique we used earlier in the semester? Do you remember that? Multiply both sides by a single term that would clear fractions on any side. So what term would that be? By which term you would multiply both sides to clear this fraction? E to the x, right? Multiply both sides by e to the x. All right, like this, like that, right? Okay, so let's simplify. On the left, e to the x and e to the x cancel each other out. We end up with e to the 2x. Let me rewrite this. Let me rewrite, and I want to save space because I'm thinking that I might run out of space here. So as I'm canceling the denominator with this, let me rewrite the numerator such that this minus e to the x is in the middle and minus 6 after that. So minus e to the x minus 6. Okay, I just switched with this term with that term. Put this in the middle, put this at the end. That's all. Okay, and that is equal to 0 times that is 0. Okay. Now what do? Do you remember one of the techniques we've used before that might be helpful here? Do you remember what that technique was? That's why I keep asking you guys to review the previous material. Remember the U substitution method? Remember that? So let U be equal to e to the x. Now rewrite this expression with u in it instead of that. Instead of e to the x, let's substitute this u in this equation. What do we get? We get u squared. If u is equal to e to the x, then u squared is e to the 2x power. Minus u minus 6 equals 0. Now that's a quadratic equality, and it's an easy equality to factor, right? So we can say u minus 3 times u plus 2 equals 0, right? U times u is u squared. U times minus 3 times 2 minus 6. Where is the minus u coming from? Well, u times 2 is 2u. Minus 3u is minus u. 2u minus 3u is minus u. So if you FOIL this, you're going to get this back. Okay? Now what? Well, by using the zero product property, again, which we learned many sections ago at the beginning of the semester, when you have the product of two factors equaling to 0, then either this factor is equal to 0, or this factor is equal to 0, or both of them are equal to 0. So let's find out when each factor is equal to 0. So if u minus 3 equals 0, then u equals 3, right? If u plus 2 equals 0, then u is equal to minus 2. Are we done? No, we just found u. We were solving for x, right? So we're not done. So let's use this with each u value to find x, right? So if u equals 3, then 3 equals e to the x. Okay? So how do we solve this for x? Do you remember? X is in the exponent. What do we have to involve? Either log or natural log. Which one would you use? Which one would you use, the log or the natural log? Well, the base of this exponential function is e, so it's better, it's easier if we use natural log of both sides, right? So take the natural log of both sides. On the left, we have natural log of 3. On the right, we have x natural log of e. We already know natural log of e is equal to 1, right? So there we have it. We have x equals natural log of 3. So that's one of the solutions. Okay? So the next solution, let's see what would be the x value if u equals negative 2. So if u equals negative 2, then negative 2 would be equal to e to the x. So this side, right there, you can see that there is no solution again. For this u value, there is no solution for x. Why? Well, because this side will never be minus 2. So minus 2 equals e to the x will never be true, because this right side will never be any negative number, let alone minus 2. The right side will never be a negative number. So this is not possible. So that is not possible. So that one, then we toss out. So minus 2 is out. That one is out. Okay? Toss that one out. Only x, the only solution of x is equal to natural log of 3. That's it. Okay? All right. So all of this was solving exponential equations, everything we've done so far. But of course, we used log because the two are related. Exponential functions and log functions, log equations and exponential equations are related. So whenever it suited us, we used the logarithmic properties to solve exponential equations. That's one of the main takeaways from this section, that even though exponential functions and logarithmic functions are inverses of each other, right? Remember when we graphed them last video? Exponential functions are inverses of their equivalent log or natural log functions. But when we solve exponential equations or logarithmic equations, they're related. We can see that they are related, and we might be able to use techniques that are from one side that can make things easier on the other side. Okay, and these examples we did are good exercise in that to see how these two are related. Now we get to logarithmic equations. Okay, these are logarithmic equations. With logarithmic equations, you must remember how to apply all those logarithmic properties we've learned before, okay, in the last class. So you must remember those, okay? So that's what I'm mentioning here in this note. I'm reminding you that you must use the properties of logarithms. That's a key to solving logarithmic equations. Okay? And also I'm reminding you here that recall the important thing that the logarithmic functions generate an exponent. With these with these kinds of equations, we must always check our answers. Always check your answers with logarithmic equations. Okay? So for example, here with the exponential function, the last one that we just did, these are rare cases which we had to pause and say, hey, if this doesn't make sense because this exponential function e to the x will never be a negative number, any negative number. So there is no solution when u equals -2. There is no solution for x when u equals -2. We had to make that check and conclude that. But usually with exponential functions, in most cases, except rare cases like this, where you have to kind of say, okay, wait a minute, this doesn't make sense. Most often, all the answers you get are valid results, except, of course, things like that. But with log equations, we must check each answer, make sure that it's within the domain. That's what I mean. Because the domain of exponential functions is -infinity to infinity. For exponential functions, the domain is -infinity to infinity. But for log functions, the domain is anything that is positive. So if I solve this and I get two values, I must check back in here to make sure that this quantity is never negative or 0, and this quantity x is never 0 or negative. That's why we have to check back. So for example, if an x value is -3, I need to toss it out, right? Because -3 plus 3 is 0, and log of 0 does not exist. It's undefined. If I get an answer that is log of 0, that x 0, again, I have to toss out x equals 0. Because log of 0 doesn't exist, right? That's what I mean. Even if I have x equals -5, it does not, I have to toss it out, right? Because -5 plus 3 is -2, and log of a negative number does not exist. That's why I say with logarithmic equations, the domain is not, with logarithmic functions, the domain is not -infinity to infinity. We must make sure that domain is never 0, never negative. Okay, that's why we have to check. Okay, so here it is, the logarithmic equation, the first one, and we're solving for x, right? And right off the bat, what I'm reminding you here, what I've reminded you here is going to come in handy. Write that statement. Recall the important thing that logarithmic equations generate an exponent. This statement right off the bat comes in handy. Okay? That one. So how is that? How can we make use of that? Well, that means that -3 is an exponent. To what base? To base 2. So what is x? X is the result. So we have 2, this base, to that power equals x. 2 to -3 power is, so that is 1 over, let me rewrite this, 1 over 2 cubed equals x. So that is 1 over 8 equals x. Okay, you can either leave the answer like that. This is the exact form of an answer. Or you can calculate it. Is it 0.125, right? I think so. Let's calculate it. What is 1 over 8? So 1 divided by 8, 0.125, right? So you can give the answer like that. In this case, this is also exact, because the decimal values end at that point. There's nothing we can rounded to. That's the full answer. Okay. Okay, so here it is again. Please pause the video and solve these three equations for x. Right? Grab a piece of a scratch paper, please. Pause the video and write those three down and solve for x. And when you're done, come back to the video and you'll see how effective this method. If you've been practicing this like I have been asking you from the beginning of the semester, you'll notice it. You'll notice how well you're learning the subject. It's because you're allowing your mind to work and do its own thinking. Okay? You're not trying to memorize what I'm writing down, which would be useless activity, but you're really using your brain here, which is really, really good, if you've been doing what I've been asking you to. Okay, so here, I'm assuming you've done that, and now you have the solutions for all these three problems. And we have one more after that on the bottom of this page, and then we have more examples. So here, we know that the natural log or log functions generate an exponent. So this minus 2 is an exponent. To what base? Well, this is a natural log, so the base is e. Even though it's not written, it's there, and it's e. So e to this exponent equals x. So that, we can leave the answer like that. If not, we can calculate it. So that's an exact answer. Or let's calculate it with a calculator. So see, just get a feel for what kind of a number that is. That has to be less than 0, right? Because of the negative, less than, I meant to say less than 1, not less than 0. But this number is going to be less than 1 because of this negative exponent. So we have e, right, to negative 2 power. So 0.13533. Okay, so I can round that to 0.13534, rounding that second 3 to 4. Let me do that. Okay, so we have x equals 0.13534. 34. Okay, either that or that. This is an exact answer. That's not. That's just decimal value that we rounded the number to. Okay, so this one, I hope this matches with what you had, by the way. So this one, let's see. Once again, we know that the log and natural log functions generate an exponent. So we know that x is an exponent, right? To what base? To this base, 125 to x power. Equals to what? Equals to this result, 1 over 25. Okay, now that we converted this to an exponential equation, we went from log to an exponential equation, right? By the way, above here in this previous answer, this should make sense because if you check, I said earlier that with log and natural log equations, we always should check the answer. So if you check, you'll know this is a positive value, right? So it checks, it's okay. Natural log of a positive value, it's okay. And if you take the natural log, you'll notice that you get close to -2, not exactly -2. Why? Because I rounded this, remember? So let's do that. Before continuing with this one, I need to do that. So if we check this answer, which is not exact, this one is exact, that one is not. We're going to get some value close to -2, but not quite -2. Natural log of 0.13534, like that. Look at that, minus 1.99999, like that. You see that? That error, the fact that it's a little bit off than -2 is because I rounded that number. That's all. Okay. So on this side, because we went from log form to exponential equation form, then the next obvious question would be, is there a way we can rewrite the left and right to the same base? Can we do that? Let's see. So 125 and 25 obviously have 5 as a common factor. So let's use that knowledge to try to write left and right sides of this equation in terms of exponential functions to the same base. Okay, so 125 to x power, 125 first of all can be written as 5 cubed to x power, right? That's the same thing as that. How about 1 over 25? Well, 1 over 25 can be written as 1 over 5 squared. And then we can move this up and make this power negative, right? So keeping the left for now the same, 5 cubed to x power equals 5 to -2 power, right? Just rewriting this like this using properties of exponents. Do you see how we're using many skills and techniques we've learned in the past? The U substitution method, the zero product property, the properties of exponents. Do you see? We're using all the things, many of the things we've learned in the past. So that's why it's so important for you to review the previous material. Okay, so we're a little bit closer to solving for x here. Again, using the properties of exponents, we know that if we have an outside power to an inside power like this, the two can multiply each other. So that means 5 can be written as 3 to the x power equals 5 to -2 power, right? Now we're getting somewhere, right? The bases are the same, so if the two sides are to be equal, the powers must be equal. So 3x must be equal to -2. Therefore, x equals -2/3. Like that. Okay? So we leave it like that. There is no need to calculate the decimal for that. I mean, if you do, probably you get something that is not exact, but I mean, something like this. So -2 divided by 3, look at that. I mean, you have to round that, which won't be exact, right? If you like, we can write it down. So this is exact answer, or x equals -0.66667, something like that, like this. Okay. If you check back, does it make sense? Yes, because this x value is negative, and it should be, because log to any base of a number that is between 0 and 1 is always negative. And 1 over 25, right? 1 over 25 is between 0 and 1. There you have it. 0.04 to this base, log to base 125. Okay, so this one, I hope you've already solved this, and I hope your solution to the previous problem, to this one, matches what I have. Now this one, another log equation, which means the log here is generating an exponent, right? We know the 3 is an exponent. To what base? Base 5, right? So let's write it that way. 5 cubed, right? This base to that exponent is equal to this result, 8 minus 7x. Okay, what do we have on the left? 5 cubed is 125 equals 8 minus 7x. This is a linear equation in x, right? We can easily solve for it. So let's do that. We have let's isolate x. So we can move the negative 7x to the left. It becomes positive when I move it, equals 8 minus 125. 125 was positive when it was on the left side. When I moved it to the right, it became negative. So 7x equals 8 minus 125, which is minus 117, right? Like that. Okay, so x is equal to minus 117 divided by 7. Let's check that in this equation. We must make sure that this number is within the domain of this log function. So when you plug this in here, you get positive 125, right? If you plug for x in this argument, then add the result to 8, you get 125 inside here. So it's okay. So this is okay to accept. Okay? Because that minus will make this minus positive. And that makes it check out as the answer. Okay, this one. And by the way, I hope that result matches your solution. And this one, So here we're asked to solve for x, but x appears in 2 terms, not 1. Can we factor x in this form? No. What else can we do? I mean, I hope I just scrolled this up, so if you haven't had a chance to solve this yet, please go ahead, solve this, pause the video, solve this, and then come back. Okay? All right, so I'm assuming you've done that, and now you're back. So, as I was saying earlier, x must be isolated if we're going to solve for it. But x is in 2 terms, which, by the way, cannot be factored. So how can I isolate x? Is there a set of tools I can use to isolate x or to do something with this equation? Yes. Last time we introduced properties of logarithms to the same base that are valid for log expressions that are to the same base, which these are, right? The base is 2. So we're fine there. Okay, so what property can I use? This is an addition problem. We can change it to a multiplication problem. So let's do that. Log to base 2 of x plus 1 times x minus 1 equals 3. Okay. Well, take a look at that. Do you remember that's one of the 3 special product formulas that I have repeatedly asked you to remember and memorize, right? X plus 1 times x minus 1. The 2 terms are exactly alike, except the sign in between is different. So what happens in this case? Well, this is a special product formula. We can then write it in this form. X squared minus 1 equals 3. So that reduces to this. You can FOIL it and get the same result, but it'll take more time. That's all. If you remember the special product formulas, especially those 3 that I asked you to, and they would be very, very useful to you in situations like this. Instead of getting confused, you can just solve the problem, which is very valuable. Okay, now what? What do we do now? How do we get this x out of this group? I mean, it's part of this group, and then it's part of the log. How do we ungroup x? We need to do that in order to solve for it. Well, remember that log and natural log functions generate an exponent. So this is an exponent to what base? To this base. So let's write it down. 2 cubed equals this result. Right? Wonderful. X squared is no longer part of that log expression. Now it's out. So we can solve for it, right? Let's do that. So 2 cubed, put all the constants on one side and separate the term with x in it on the other. So 2 cubed plus 1, right? Minus 1, I moved it. It became plus 1 equals x squared, right? So what do we have? On the left, 2 cubed is 8 plus 1 is 9 equals x squared, right? So what do we get? Take the square root of both sides. Is this correct? Is this correct, or there's something missing? We're taking the square root of both sides. Do you remember the square root property? Do you remember what that tells us that we need to have? We need to have plus or minus unless the square root that we're taking is giving us a value for a distance, like the radius of a circle or the distance between 2 points. In cases like that, those are exceptions. Distance can never be negative. In cases like that, we toss out the negative answer and we keep the positive one. But this is not about distance, right? So we have to keep both solutions. So x then is equal to plus or minus 3. Okay, should we accept these two answers? Let's see. We need to check. Positive 3, plug it in. Does it make sense? 3 plus 1, positive 4. Yes. 3 minus 1, positive 2. Yes. How about minus 3? Minus 3, plug it in. Minus 3 plus 1, minus 2. Log of minus 2? No. Log of a negative number does not exist. So the minus cannot be accepted. So x equals minus 3, not acceptable. Not acceptable here. But x equals to 3 is acceptable, and it checks out. Okay? This is why with logarithmic equations we need to check to make sure that these numbers, the solutions we have, are within the domain of the log function. Okay? All right, so here we have a log equation. Look at where x appears. X appears in 3 spots, right? Here, here, here. And when we solve for x, we need to isolate it. So what should we do? How do we isolate? We can't factor anything. How do we get x out of this situation where it's in three spots, but we want it to be in 1 spot because we need to solve for it? Okay, we can't factor, but we need to ungroup x. So let's apply the relevant properties of logarithms. Let's apply those. Okay, so this is a subtraction. On the left, we have a subtraction of 2 log functions. So let's combine it into a division problem. And we can do that because the bases are equal. If this base was 3 and that was 5, we could not apply the logarithmic properties. Remember that. The logarithmic properties are only applicable if we have equal base for the log expressions. So, changing the subtraction to division, we have log of x plus 14 divided by x plus 6, 2 base 3. On the other side, we have log to base 3 of x. Okay. Now what do we do? Well, let me bring back that first page, the first page of this worksheet. Do you remember this box? Property of logarithmic equations. We said that if we have log of m to some base and log of n to some base, then m and n must be equal to each other. There is no other way the left and right can be equal, right? If the log of m and the log of n to the same base are to be equal to each other, then the m and n must be equal to each other, which is that. Okay, let's make use of that. Log to base 3 of this whole thing is to be equal to log of x to the same base 3. So that means this, so in our case, this is m and this is n when you compare it with what we have on the first page, right? So we must have, so let me write this down. From the first page, we must have m equals n, right? All right, so let's do that. By the way, I forgot to mention it, but I hope that you have solved this ahead of me. You paused the video, you solved this, and now you're back, I hope. So then let's set these two equal to each other. X plus 14 divided by x plus 6 equals x, right? So this is a rational equation. Several sections ago, several lessons ago, we learned how to solve these, right? Well, how would you solve this? Multiply both sides by what would clear the fractions, right? In this case, it would be x plus 6. So x plus 6 times x plus 14 divided by x plus 6 equals x plus 6 times x. Okay. Well, this x plus 6 and this x plus 6 cancel out. On the left side, we have x plus 14. On the right, we get x times x, x squared. X times 6 plus 6x. Right? Let's move everything. This is a quadratic equation, right? So let's move everything to one side and set it equal to 0. So x squared plus 6x, I'm going to move these two to their side. X is positive on this side. When I move it, it becomes minus x. 14 is positive on this side. When I move it, it becomes minus 14 equals 0. So let's combine these. We get x squared plus 5x minus 14 equals to 0. This is a quadratic equation. You can either use the quadratic formula to solve for x, or you can use the factoring. But these numbers are easy to find factors for, right? So this is simply x plus 7 times x minus 2 equals 0, right? X times x is x squared. 7 times minus 2 is minus 14. Where is the 5x is going to come from? It's going to come from x times minus 2x is minus 2x plus 7x. 7x minus 2x is positive 5x. So we got the factors. Now, if x plus 7 equals 0, we get, now applying the zero product property, right? X equals negative 7. If x minus 2 equals 0, then x equals 2. Can we accept both? No. We need to check. So, Negative 7 in here, would it check out? Yes, negative 7 plus 14 is positive 7. So negative 7 is within the domain of this one. Then what about here? Negative 7 plus 6. Oops, it adds up to negative 1. Log of a negative number does not exist, so we cannot accept this negative 7 answer. So this one is outside of the domain of the original function. We toss it out. How about 2? Let's test it. 2 plus 14, 16, that's a positive value, so it's okay. 2 plus 6 is positive 8, that's okay. 2 log of 2 to base 3, it's okay, it's positive. So this is the only answer, x equals 2, that checks out. Okay, we toss out the negative 7 answer. Okay, so in this example, here, go ahead, these last two problems, go ahead please and write these on a piece of scratch paper, solve them, find the value of x, and then come back to the video. I'd say if you're doing good, solving these two should take you about 10 to 15 minutes. No, definitely no more than 15 minutes. But if you're a little bit slower, but still it's worth going through this on your own without looking at my solutions. Okay? It doesn't matter, even if it takes you half an hour, but don't go beyond half an hour. Okay? And then come back to the video. All right, I'm assuming you've done that, and now you're back. So here, we're solving for x, and again, x appears in two spots. We need to isolate x. One thing we can do here is use the properties of logarithms and natural logarithmic expressions, right? So this is a subtraction problem. We can change the left side to a division problem. So natural log of x plus 1 divided by x, right? That's using the properties of natural logarithms. Then on the other side, we have natural log of 4. So what do we do now? Well, let me remind you of this property of logarithmic equations that on the first page that said if you have two log expressions in an equations that are said to be equal to each other, then m and n must be equal to each other. Otherwise, their logs would not be equal to each other, right? But of course, they must have the same base. Is that the situation we have here? Absolutely. We have natural log. So the base on both sides are equal to e. So in our case, this is m and this is n, the 4. So once again, from the first page, we must have m equal n. Okay? All right, so let's set these two equal to each other. M is x plus 1 divided by x equals to 4, right? This is according to the property we have on the front page. So this becomes, all of a sudden, using that property, this natural log equation turns into a rational equation. Do you see the transition? And we already know how to solve rational equations, right? We talked about them sections ago. So the first thing is get rid of the fraction. How do we do that? We multiply both sides by the single term that would clear any fraction and all fractions on all sides. In this case, we have this one fraction, right, like this. So let's put the rest of this solution here, over here. Okay. So on the left, the x and this x cancel out. We get x plus 1 equals 4x, right, on the right. So this is an easy linear equation. We have 1, 4x. This x, let's move it to the right. It was positive. When I move it, it becomes negative x. Then we have 1 equals 3x, and x equals 1 over 3, right? Because to isolate x, we need to get rid of this 3. So divide both sides by 3. So let's quickly check this to make sure if there is no problem with it. 1/3 is a positive value. We plug it in here. We get 1 plus 1/3, which is 4/3, right? So it's okay. Minus natural log of 1/3, again okay. So this checks out. This x value is within the domain of the natural log function we have. Okay, this 1/3 does not make this expression equal to 0, and it does not make this x equal to 0, and it's not making this one negative, and it's not making that negative. So it's within the domain of the natural log function. I hope this is the answer you got. Okay. This one. So I'm counting on you that you already have the solution for this one. Okay. All right. So let me present my solution then. So take a look at this. We're solving for x, but x appears in 3 spots. And you know you've got your work cut out for you, because if you're solving for a variable, you must isolate that variable. And this is scattered all over the place. Well, let's see if applying the properties of logarithms can help us isolate x here. So on the left, we have 2 natural log functions being added. So we can use that property we have to multiply the arguments here, the arguments being x plus 8 and x minus 1. So natural log of x plus 8 times x minus 1 equals, on the other side, let's apply that property we have. This number in front can become the exponent. So natural log of x squared. Okay, once again, let's remind ourselves about this expression. And this is, by the way, true for natural log. It doesn't make any difference if you have log or natural log. If you have log of something equal to natural log of something equals to natural log of something else, then those arguments are m and n, must be equal to each other. It does not matter if this is a log or natural log. So now we have the same situation here, where the base here is e, because this is a natural log. So the base is e. The bases are equal. So we can apply that property. And in this case, m is that whole thing, and n is this whole thing. So let's set both sides equal to each other. So m, as we explained in the previous 2 examples, m should be equal to n. So x plus 8 times x minus 1 must be equal to x squared. Right? Okay, on the right, we're okay. But on the left, we need to free up x, right? X is now part of this group and that group. We cannot isolate x if it's part of groups. So how do we free up x? We should FOIL this. We should distribute these terms. So x times x is x squared. X times minus 1 is minus x. 8 times x is positive 8x. 8 times minus 1 is minus 8. Equals x squared. Well, let's move everything to one side. I'm going to move this to the left and set the right equal to 0. So x squared minus x plus 8x minus 8 minus 8x squared, that's that one that I moved to the left, equals to 0. Let's simplify. x squared and minus x squared add up to 0, right? Then 8x and minus x add up to positive 7x. Minus 8, right, which is the only constant in this equation, equals 0. Well, now let's solve for x then in this simple linear equation. So we have 7x equals, let's put minus 8 on the right. Let's move it to the right. When I move it, before move it was negative 8. When I move it, it becomes positive 8. So x, is x isolated? No, it's got a 7 next to it. So in order to isolate x, we need to divide both sides by 7 to get rid of that 7. So we end up with 8 equals 7. 8 over 7. Okay, that. So let's see. Let's check back into the original equation, making sure that this x value is within the domains of these natural log functions, each of them. So 8 over 7 plus 8, that's going to be a positive value, so it's okay. 8 over 7 is a little bit over 1. In fact, if we calculate that, what do we get? Right? 8 over 7 it's 1.1428 something. So if you plug 8 over 7 here and subtract 1 from it, you get a positive number, right? So minus 1, we get 0.1428. That's a positive value. So again, this number is within the domain of this natural log function. So it's again okay. 8 over 7 in this x, again, that's within it's a positive value. So when you plug it in here, it's within the domain of this natural log function. So this answer checks out. Okay. Okay, so we have come to the conclusion of another section. I hope this was useful. I'm sure it is useful if you take my advice and pause the video repeatedly, use your own skills to solve these problems, and then look at my solutions. I am 100% sure you will walk away from this class very confident about this material and very happy with the grade that you're going to get. Okay? So please resist every temptation to look at my work without having written down your own solution first. Resist every temptation to that. First, solve these problems on your own. All right, thank you again for persisting through another video. And for now, have a nice day, and I'll see you again next time.